It's fantastic to be here. Not the least reason being, I live in Chicago, and if you look here, the weather in Chicago is -2, very cold, and in Taipei, it's a beautiful 29 degrees. So I'm super excited to be here. But it's not just that. I mean, it's a fantastic opportunity. So once again, thank you for all the organizers. Thank you most importantly for all of you to be here, for your interest in Connect. What I want to do actually is sort of pick up exactly where Stuart left off. Normally I sort of get into my slides, but since I have internet access, I wanted to show you something really quickly. The site that Stuart mentioned, connectforwindows.org, basically is a great resource. And I see a lot of you here have laptops, so I want to make sure to point this out in case you want to get the source code and or the SDK and play along as we proceed. I'm on internet. It worked there just 5 seconds ago. Everything was working great, and now it won't go. This is crazy. Actually, let me see if I fold it up. Okay, so the key, we'll see if it comes up, but the key thing I wanted to point out was on the tab where it says resources, you can actually see all of the other Connect projects from the Channel 9 gallery that Stuart was talking about. So the goal of my session, there it is, thank you. So obviously this is the home page, right? And you can download all of the SDK by clicking that one link, depending on if you have a 32-bit or a 64-bit computer. It's just one download, and it's a very reasonably sized download. It's like 20, 25 meg or so. But if you get over to the resources section, this is fantastic because it has a bunch of really cool links to for additional follow-up. So you have a few links to the forums. If you have questions about some features, the forums are a great way to see if somebody else has had the same question and if it has already been answered. But more importantly, it gives you a couple of links to the project gallery and quick starts. And I'm going to just wait for these to come up. So this is basically what Stuart was talking about. This is a gallery of about 100 different applications from around the world built on the Connect. Most of these have the source code, right? So the really cool part is actually you can look at a full-fledged application that somebody else has built, including the source code. And as most of us in software realize that one of the best ways to learn is by looking at other people's source code, is by looking at samples. So definitely take advantage of that. So if you're here, if you have a computer, if you have internet access, and if you haven't already received or downloaded the SDK, go and do that, and then check out some of these resources. The final thing I want to show on the website is a bunch of hands-on labs that there are, and this is great. In fact, let me show you a very quick example of the skeletal viewer walkthrough, if you will. You can download either a Word or a PDF file, and what this is a step-by-step walkthrough of the sample that comes with the Connect SDK. So let me just open it and show you what is inside. And the reason I'm showing you all of this is these are perfect resources for you to explore right after we leave here. So Microsoft and the community around Connect has provided a bunch of resources to sort of take you step by step through the whole learning process. So don't feel that what you see and hear today is sort of the end of the road. There's a lot of support that you can count on. Okay, so while all of that's happening, let me bring up my slides. And the final thing I want to talk in terms of resources, the final thing I want to mention also is my email address. So my name is Krishna Kumar, and my email address is just my first name dot last name at microsoft.com. So if through the course of the day or after today, if you have any questions that has not been answered and you cannot find what you're looking for in the resources resources we looked at, please definitely feel free to reach out to me. I'll be more than happy to help answer your question. If I cannot, then I know a few folks like Stuart and a few folks in the actual product development group that can help answer the question. So one way or the other, we'll make sure that your questions are answered. And the reason again is because we want you to be involved in the Connect space. And it is, basically the power of the community that's going to make the ecosystem really rich. And so we want to see how you take this and where you take Connect. So with that, I'm going to step right in. I'm going to skip through some of these positive feedback, and all of that. As you can imagine, it's been huge, right? I mean, the potential of Connect, everybody realizes it's just going to be one of those big, game-changing products. You saw some of the videos before the session began in terms of some of the things that you can do with the Connect, which just a couple of years ago was almost impossible, right? Imagine a small, simple consumer device like this being able to do really sophisticated things, like not just give you a video image like a webcam, but also give you 3D data, direct 3D streams, and more importantly, be able to do things like skeletal tracking, so understand the human shape and figure out what the human shape is doing. All of that really, a couple of years ago, was unimaginable in a non-researchy or a very non-exclusive setting. But today, everybody has one of these things. And at the price point that the Connect sells for, between $100 to $120 US, and based on the statistic that Stuart showed us in terms of Connect being the fastest selling consumer device in history, we can pretty safely assume that this device is going to be one of those pervasive devices. It's probably going to be as pervasive as a TV is today. So what that means for you as researchers, as future developers, is that you can build experiences that can be consumed by a huge variety of people, right? So if any work that you do here has a really large audience, so I really encourage you to think about it that way. And we've tried to make it really easy for you to target the Connect, right? So it's not just on one specific language or one specific IDE that you can use. We've basically made it available for both managed developers, unmanaged developers, so whether you program in C++, C and C++, or any sort of .NET language like C# or VB, or even any of the other .NET languages like F# or whatever, you can target Connect, right? And we've basically made sure that any investment you made in learning Microsoft technologies is directly transferable to the Connect. So for instance, if you would, with Visual Studio, to build, games or websites or anything, the same experience, the same tool set can be used to build Connect applications. So any investment in the Microsoft developer technology space translates directly to building GUI applications, natural user interface applications on the Connect. Additionally, we also saw a bunch of samples and resources that are provided. And the URL I should mention again is this redirects to the new URL, which is connectforwindows.org. So let's get to look at what is on the Connect and inside the Connect for a few seconds. So you're seeing a Connect in front of you, and you're also seeing a picture, but let's look in some more detail to what there is. As you can see, there are basically three reticles, if you will, right? Three ports. And it seems like there's three cameras, but basically what's happening is the center one is just a plain RGB camera. It's almost like a webcam on your computer. It basically looks at the scene in front and returns a color feed in RGB format, red, green, and blue format. The surrounding two reticles, this guy and this guy, are actually a combination 3D camera. And the way it works is, on the left here, this is basically a 3D projector. It's a very small laser, it's a very low power laser, infrared laser that emits a pattern in the scene in front of it. And if you're concerned about, it's emitting infrared and is it safe and all of that, let me assure you by saying that the power of the infrared laser is a fraction of what the infrared we receive just by heading out in sunlight. Right? So you receive orders of magnitude more infrared by just stepping out of this building than from this laser, so it's perfectly safe. But what happens is, this laser emits an infrared beam into the space in front of it, and this camera is an infrared camera that reads the pattern back. And based on the difference between what is projected and what is read back, it'll perceive depth information, which we'll see in a second. There are also, like Stuart mentioned, an array microphone setup. So there's actually 4 separate microphones that are on the Kinect. There's one here, and 3 sort of here. But all of them work as a single microphone, as a single array mic. And we'll see some of the benefits of that in a second. And the final hardware subsystem is actually a motor, a very small motor that's in the base right here that allows the Kinect to swivel up and down. So that if the Kinect needs to get a better view of what it is seeing, it can swivel up or down and so on. But this is basically it. This is all of the components inside the Kinect in terms of the hardware, right? There's nothing else that we aren't showing you. Everything else that happens is sort of the magic of software that we will explore in a second. So just a quick summary of what we saw. A regular camera, a 3D camera, which is a projector and a receiver system based on infrared, a microphone array, and a tilt sensor, a tilt motor. So the one thing I want to mention is the pitch. If any of you is wondering how much does it go up and how much does it go down, it's plus or minus 27 degrees. So it gives you a total angle of movement of about 54 degrees up and down. So let's take one step closer to how the actual 3D depth sensing works, right? This is, when somebody looks at the Kinect for the first time, 2 things really stand out in terms of what Kinect can do that nobody else today in the commercial space can do. One is, cheap 3D sensing, right? Inexpensive 3D sensing, and 2 is skeletal tracking. So the way 3D depth sensing works is very similar to the way the human visual 3D sensing works. The way humans actually perceive 3D is most of us, or all of us have 2 eyes, and the image that comes across to our left eye is slightly phase shifted from the image that comes across from our right eye, right? Because they're a little apart, images are slightly apart as well. And so what happens is the brain actually can see the phase shift, and from that shift make sense of the 3D space in front of the human. The exact same principle is deployed in the Kinect, right? We look at how the projector and the camera work together. Basically, the projector projects a beam, and the projector projects a known pattern in the scene in front of the Kinect, and the camera reads the pattern back. Now, the pattern actually is going to be distorted or deformed based on the 3D scene in front of it, right? So, and we've seen this happen, right? Imagine just a regular projector like this. Now, if there's no, if there's no object between the projector and the screen, you basically see a clear image like this. But if I were to walk in front of this scene or in front of the screen, part of the image falls on me, and then part of the image falls on the screen, and there's a distortion that you can see. And so based on reading that distortion of projected images, Kinect actually can calculate the 3D scene in front of it. And this, I want to emphasize this because a lot of people have this misconception that the Kinect does 3D sensing using time of flight, which basically is how long does it take a projected beam to come back to the Kinect. It actually does not do time of flight calculation, it does distortion-based calculation. So this is basically what the pattern looks like. It's normally invisible, but if you have an infrared lens or an infrared camera, you can actually see the pattern as it gets projected out. And this is what it looks like. And if you look at it closer, it's just basically a bunch of little pixels that are spaced apart in a known pattern. That's basically what's happening. So that was some of the technology inside the Kinect. To actually start programming a Kinect, obviously, you need to be able to connect it to your computer and install the SDK. The one thing I want to mention is some of us actually, if you buy a Kinect packaged with an Xbox, you probably need another cable because the connector only is meant to connect directly into the Xbox. Now this will change with the new hardware that Stuart talked about that is coming soon. But if you have a Connect today that came packaged with your Xbox, your connector is not a USB connector. It will not plug into your PC. So what you'll need is a separate cable, which is what I'm picturing there, that basically has a connector and a USB connector. So it acts as a power cable and as a bridging cable between your Connect and your PC. But if you got your Connect standalone, you already have this cable. So that's one thing I wanted to mention because sometimes people come and say, does it plug into my PC? What do I do? So I just want to explain that. Don't force it in. Right. Okay, so once you install your Connect onto your PC, it's just like any other USB device. Windows will actually install the drivers and make the devices ready to use. So with that, let's take a brief look at one level deeper inside the Connect, and this is sort of a dissection of the Connect, if you will. When you take the top off, when you take the cover off the Connect, this is what you see inside. It's basically, it has what seems like 3 separate boards, right? 1, 2, and 3. But it's actually just a single board with all the components on it. Now, because such a big board wouldn't have fit, it basically sliced it and put them in slices with connectors underneath. But basically, the hardware just is what we looked at. It basically has the VGA camera and the infrared projector and the infrared receiver. These are what the actual components look like. And I'm showing you this just because you don't have to go dissect yours and see what's in there. The spare file we came through. This is the lab document I was talking about in terms of walking through some of the samples, and you can see how much detail we provide in terms of the sample. So you can basically see it gives you source code, it explains the source code and stuff like that. So provides a lot of information, so check it out. But back to our presentation slide deck. So yeah, these are the 3 camera components. And so what the camera components allow you to do is literally this. The RGB camera returns a color feed, just like a regular webcam. And the depth camera actually returns a depth feed. It's not exactly this that it's returning. What it is returning is just a series of numbers, right? What the format of the data that comes back is like this. For every pixel that it's reading, for every pixel in the frame, it tells you the distance from the Connect in millimeters of the nearest object in front of the Connect. Does that make sense to everybody? Yeah? Okay. So it basically gives you a set of depth information, which you can then take and convert it into an image like this, or use it for whatever else you want to do. So in this case, they've taken the depth information and made it into a monochrome image where the objects that are closer to the Connect are represented in shades of, in lighter shades, and objects that are farther away are represented in darker shades. And you can actually see this person is standing closer to the camera, so that he appears lighter than the ballerina, who in turn appears lighter than the actual back wall, which is all black. So literally, this is what you get from the depth camera. You get distance readings for every pixel on the frame. So that is basically what you get from these cameras. The other element, like we saw, is the actual microphones, and this is their placement. You basically have 4 microphones, but instead of being uniformly placed, they're actually placed in a sort of a staggered fashion. What that allows you to do is by getting the feed, the signal strength from each of these microphones, it allows you to identify where the speaker is. Does that make sense? Right? If somebody is closer to this side, the signal in this mic is going to be a lot more than the sort of the signal strength in these mics. So the software allows the Connect to identify where the user is. Right? It allows what we call beamforming to happen. So for instance, if somebody is here and speaking, then this mic will pick up a louder volume than this mic, and so the Connect knows that the sound is coming similarly, if the user moves, we can keep track of where the user is at all times. And this has a big advantage, right? One of the biggest advantages is of having this multi-array microphone and being able to do beamforming is it allows us to do something called sound isolation, right? We can basically identify and isolate the primary speaker from all the background noise. Just because we know where the speaker is, we will focus on that feed alone and sort of remove all of the background echoes. So to give you a quick demo of what that sounds like, let me play this for you. So this is a quick demo of the echo cancellation that happens inside the Connect. So what I'm going to do is I'm going to play you two sound clips. One is the actual raw sound clip. That is basically the pre-echo cancel sound clip, and then the next sound clip I'm going to play for you is the sound clip that you get after it's been cleaned by the Connect.
This is an example of multi-channel echo cancellation, extracting my voice from the game sound.
Right, so this is the actual setup, and then after the echo cancellation happens.
This is an example of multi-channel echo cancellation, extracting my voice from the game sound.
Do you see the difference between the two? You see how much cleaner it sounds, and that's because of the multi-array microphone and the software that's inside the Connect that's doing this for us. So that was basically what we've looked at so far is all about the hardware, right? We've looked at the cameras, we've looked at the feed that comes back from the cameras, we've looked at the microphones, and we've looked at the feed that comes back from the microphones, right? Now let's sort of see how it all comes together when you start programming it using the SDK. So when you install the SDK, this is sort of a figurative way to look at what gets installed. So the base is obviously your hardware, right? This is the actual Connect device. One of the things you'll see is the Connect device has a USB hub built in because it has, you remember we talked about how the Connect has 4 separate hardware devices, the VGA camera, the depth camera, the multi-array microphone, and the motor. All of these are separate USB devices. But you only have one USB cable connecting it to your computer. So what happens is the Connect has a USB hub inside, which takes that USB connection from your PC and spans it across all of the different hardware devices inside the Connect. So, and that's the reason, one of the reasons why you will see us mention do not connect the Connect USB port into a USB hub, always connected straight into your PC, and this is the reason why, because there's already a hub, it's already going through a hub inside the Connect, and if you basically connect it to another hub, then the bandwidth will become too low to sustain the data streams coming from the Connect. But above the hardware layer, this line basically is sort of symbolizing the difference between the hardware layer and the software layer. But right above the hardware are the actual drivers for the Connect, right? So you basically have drivers for your cameras, the drivers for your audio subsystem, and so on. And above the drivers lie the actual SDK to program the camera streams and to program your audio streams. Now the key thing I also want to mention is for the audio segment, the Connect SDK relies heavily on the audio SDK that ships with Windows, right? Because Windows has for the longest time supported microphones and audio streams and even multi-array microphones. So it basically uses the same speech technology that Windows uses. So what that means is if you're already doing any sort of audio work, if you're already using an external multi-array microphone, you're running programs for that, for about 95% of the functionality, you don't really have to make any changes to get it to run when they connect. Because ultimately the SDK is still the Windows SDK, and so the code will run unchanged. The only programming that you would probably have to do is for the vision component of the Connect. And the top layer obviously is the application UI on top of the SDK. Any questions so far? Okay. So again, a quick recap. When you install the SDK and start programming the Connect, what do you get? You get two raw streams. You get the raw stream from the RGB camera, from this camera right here, which is the video camera, and then you get the raw feed, depth feed from the 3D camera pair. Apart from the raw feeds, you can also get the skeletal tracking capability. If you turn on skeletal tracking on the Connect, you can also get the skeletal feed from the Connect. Now, obviously, the skeletal feed is a processed feed, right? So what Connect does is inside the Connect, it takes the raw feed, the depth feed, and as Stuart mentioned, it basically analyzes it frame by frame, segments each frame, actually analyzes each frame to see if there's any human characters in the frame, and then for each human character in the frame, it segments it further into different body parts and different joints. And all of that resolved joints is fed, can be accessed by the SDK in your own application. So the point I want to make, and actually to an earlier question of how the SDK is different from OpenNI and all of that, I said this is a big distinction, right? Because it's the official Microsoft SDK, we are probably the only group that's able to provide you with not just the raw feeds, but also all of the process information that comes from your Connect. So this is a huge advantage. So apart from getting all of the camera feeds and the process skeletal feeds, you also get obviously the raw audio data that comes from the Connect, and you also get the processed beamforming data that you get from the Connect. Does that make sense? You get the actual raw stream, and you also get the processed information in terms of is your user here or is your speaker here, and so on and so forth. So literally from the SDK, this is what you receive, right? And this allows you to sort of plan in terms of how to build your application. So with that, we are ready to sort of step one more layer into actually looking at programming and Connect. But before that, I just want to pause for a second and see if there are any questions. So basically, to summarize, what we've seen so far is we've seen what's on the Connect, what the actual hardware device has, and how the software SDK exposes all of that functionality into your application, right? The next step now is going to actually see it in action. We're going to be able to write some small pieces of code to understand how to retrieve the raw feeds, how to retrieve the processed skeletal information, and incorporate it into your application. Now, the key thing I also want to mention is all of this, like we saw earlier, is available across a bunch of different languages, across a bunch of different project types. So these could be games that you're building, these could be Windows Forms application, these could be WPF application. Any type of application that you build on Windows can access all of this, right? So just because we build a particular type of application today, or the samples, build a particular type of application, do not assume those are the only types of apps. You can actually incorporate this in any type of app that you're building, any type of client app that runs on Windows 7 or Windows 8 can take advantage of all of this. So if there are no questions, I'll go with yes.
How do you get the depth information, right?
Right.
Depth information. How does the information come from? By calculation, the depth, you get the depth information.
Right.
But where's the calculation done? Where is the calculation being done for getting the information?
The depth information. Okay. Yeah. So the calculation is done inside the Connect.
Inside the Connect. So there was some processor or CPU inside.
Yes. So the let me step back a little bit. You see these three boards right here, 1, 2, and 3. That has a CPU and processing inside the Connect. So in fact, not just the depth calculation, all of the skeletal tracking that happens frame by frame. A lot of that, especially when it comes to a PC scenario, a lot of the depth calculation, all of that's done there. So what comes into your PC is basically the But figuring out if a particular pixel is 1 meter away or 2 meter away, all of that is done inside the connector. In fact, we'll see some as we go a little further. We'll actually see that for a skeletal tracking, for instance, the Kinect can only skeletal track 2 people, 2 primary players, in terms of breaking down that player into the different body joints, and that 2 limitation is regardless of whether you connect it to an Xbox or to a PC or any other device, regardless of how fast your PC is, because again, all of that happens inside the Kinect. So it's basically a bandwidth of the device and the CPU inside the device and not your PC. So yeah, all of that is inside the Kinect. Any other questions? Yes, sir.
Hello.
Yes.
I have one question. Why the resolution of the RGB image is different from the depth map?
Right. That's a great question. So basically, for 2 reasons actually. The RGB, in fact, while I call out the fact that it's 640 by 480, that's the native resolution, but it can also support 1280 by 1024 actually. It can also support a higher resolution. But the highest depth resolution it can support is 320 by 240. And this is because, for 2 reasons. One, through the product development phase, they actually found that this resolution of 320 by 240 is adequate to give you sort of a high fidelity joint recognition and representation. And 2, for the performance characteristic, if you make this any larger, then it sort of exponentially takes up more cycles to process. Because unlike the RGB image, which is just basically what the camera sees is what it sends out, for the depth image, it actually goes through a pipeline, right? It basically takes the scene it's seeing, and then it has to basically go to each pixel and identify how far away that pixel is from the camera. And so if you increase this to say 640 by 480, the amount of pixels and therefore the amount of processing that needs to happen increases exponentially. It's sort of a geometric expansion if you increase the resolution. But in also the fact that in testing they found that because we're dealing with sort of known shapes like human subjects, right? This resolution provides high enough fidelity to distinguish different joints. But you're right. I mean, if this had to be expanded to be able to detect unknown shapes, like random shapes, then we might need a higher resolution display to work with. But because it's a known target, because there's a lot of machine learning work that already went in to look at what looks like a body shape and segment it further, it allows us to work with sort of a slightly lower resolution image and processing. The biggest advantage is speed. It allows us to process it way faster than processing 640, 480 or a 1280.
I have another question.
Yes.
Yeah. So the limited is from the USB broadband or something?
The limit for
Because the resolution, you have reduced the resolution to process all those things.
right, it's a CPU limitation more than a bandwidth limitation.
CPU limitation.
Right.
Yeah. So if the CPU is soon enough, is speedy enough, yeah. So can we parallel to two or more connect together to increase this resolution?
So yes, you could technically you can chain 2 or more connects. But I am not clear in terms of how that would help us get a higher resolution 3D depth map, because both the connects would still be operating at 320 by 240, and so if they're looking at the exact same identical scene, the feed you would get from both is going to be identical, right? In the cases where we see pairing and chaining of connects happen is when you want to cover a wider angle than what one connect can provide. So say for instance, a Kinect, I think, typically has a 120-degree field of view. And if you want to get a 360-degree perspective, I can chain 3 Kinects together, one looking here, one looking here, and one looking here, and get a full 360 perspective of the scene. But your perspective's resolution is still going to be 320 by 240, and that's going to be the maximum resolution you can achieve.
Maybe for the use of motion capture. Because if you got just one camera,
Right.
or one Kinect, you maybe with some angle from your movement, your point was high. So if you got more than one camera, you can catch all the angle
Absolutely, yes.
of your body.
Yes, you're right.
So I think can we do that?
You can absolutely do that. So to your point, if I have one Kinect like this looking at me,
Yeah.
it can only see from here to here. It doesn't know what's happening here. It doesn't know what's happening behind me.
Yeah.
But I can have another Kinect here and another here that can see all of me.
Yeah.
You can absolutely do that.
So from now on, the SDK, Microsoft SDK can do these things right
Yes.
now.
The Microsoft SDK, the official SDK can
Yeah.
support Kinect chaining and can support getting streams in parallel from multiple Kinects at the same time.
Yeah. How much device the SDK support? How much?
How many? That's a good question. In terms of theoretical maximum, I mean, we've never seen anybody use more than 3, just because each Kinect gives you a
Maybe
one.
we can try. I just
Right.
want to know if there has any.
There's no theoretical maximum. It's limited by your USB bandwidth on your PC. Because each device has to go in its own USB connector,
Yeah.
and your USB bus on your PC should be able to support all of these. Because this is a pretty high bandwidth device, especially if you turn on all the streams, it can get high bandwidth. But as far as I know, there's no theoretical maximum. But we've never seen a case, and maybe those cases will emerge, where if you're trying to cover a huge stadium or something, for analysis of batting and sports and all that. But we've seen about 3 or 4 Kinects chain at the moment. Basically.
Thanks.
No problem. Thank you. So, any other? Yes, sir.
Because your SDK provide the registration information between these 2 images for registration. There can be some disparity and also the resolution.
Right. So the question was, just to make sure I got it right, was the question, does the SDK provide registration information, like
Yeah, like which pixel of this
corresponds to which pixel of this?
And
Absolutely, yes.
some disparity.
Yes, you're right. Because so the question was, does it provide sort of a cross-reference system between your VGA feed and your depth feed? Yes, it does. So there are, and the reason that's a great question is because of the fact that if you look, the VGA camera is here and the depth camera is actually here, and so there's a slight phase shift between the VGA camera and the depth camera. So if you try to overlap your depth camera on top of the VGA camera, you'll find a very small shift. And so the Kinect SDK provides a method call that allows you to extract the right pixel from the VGA camera for every corresponding pixel in the depth camera. It also allows you to synchronize the VGA camera and the depth camera. In fact, so let me show you something here. You see, actually, even though we show all the camera as a single packaged box, the fact is that the VGA camera, see it here, the VGA camera actually connects through its own USB connector inside the Kinect than the depth camera does. So these are actually, if you think about it, 2 separate cameras. And so what we do to make it easy for you to program applications, we provide information like frame numbers and timestamps that allow you to correlate the image that's coming from the RGB camera with the image that's coming from the depth camera. Because it's almost like having 2 separate cameras connected to your PC and trying to correlate the frames coming from each of those cameras. So yeah, we provide all of that information. I'll make sure to point that out as we start programming the SDK. Any other? Yes, sir.
Yes. understanding that Connect just provide 3D spatial information of each joint. So my question is that when our object just turn around, when you just has its back facing the camera,
Right.
can this system can tell the difference of the back facing or just front facing the camera?
That's a great question. So the Kinect sensor cannot tell the difference between front facing and back facing, because interestingly what happens is, like actually Stuart mentioned, all of the skeletal processing that happens on the depth frame alone, right? And so the depth frame has no notion of whether it's front or back. If it detects a humanoid shape, like like a human shape, like a head and shoulders and hips and all of that, it's going to assume it's a human and do skeletal tracking. So we'll actually, when we write the code, we'll actually see if we can demo this. I could stand with my back to the Kinect, and it will still assume that it's looking at me from a front perspective. And that's a great question, but the reason we haven't supported that is because it started off as a gaming system. There are very few, in fact, I can't even think of a case where you would need, you have your connector and your TV there, and you would need to have your back facing the connector, the TV. Does that make sense? But from a perspective, but no, in all seriousness, from a GUI perspective, it makes sense. Spatial awareness is important, but in terms of the current implementation of the Kinect, it does not distinguish between front versus back in a humanoid shape.
We're now developing a rehabilitation software to handle this issue, but the rotation of the patient plays an important role. So I'm sorry that because we found that OpenNISD can tell the difference. They just provide some rotation information.
Absolutely.
Yeah. The second question is that I just found if the patient is just laying down, can just connect it has a precise detail, still can acquire the joint information precisely.
So
laying down.
did you want to make a comment?
Yeah.
The second part or the first? Like, did you have a comment on the first part?
Oh, rotation.
When the subject is rotated?
Come back.
Okay. So we'll get Stuart's perspective on the rotation aspect, but for a subject actually laying down, it depends. So one of the things we've seen with sort of just playing around with the Kinect is it's pretty resilient to what you do after it has tracked you. So for instance, the initial skeletal tracking will only work if it can see 2/3 of you. So from your head to your knees, at least, it needs to be able to see to identify it as a humanoid shape and start tracking joints. Now after that, you can actually, get partially clipped from the frame. So you could basically exit the frame and just have, maybe say your shoulder to your hand showing, and it will still track you. It will still basically give joint information. Because along with the joint position information, it also assigns a probability value in terms of how accurately it thinks the joint is where it says it is. And so if it can see the joint, it will basically assign a probability of 100%. But if it cannot see the joint, it can actually infer where the joint should be based on the other joints it can see, and so it will assign a lower probability. So it can do that pretty well, even when you're not in a standing position, even if you move around a lot. But if you lie down, it depends on what it can see of you. So for instance, if the Kinect's looking and I'm lying down like this, and if all it can see is my right-hand side, it'll lose track, obviously. But if I'm lying down, where it can still see, a portion of my head, a portion of my torso, and a portion of my legs, it'll actually go into the track. So that is sort of the point I would make. However, the 3D subsystem will still give you all of the 3D data. So if you find that your application requires a user to be sort of in a non-conventional state, like not standing or not sitting, then it should be, and if you find that, if your application is consistently going to be used by a user being in a particular position, then it's pretty straightforward to actually code it up manually through tracking yourself, because all of the raw streams will keep providing you, even if we cannot do skeletal tracking on it, if that makes sense.
before I come here, because we are not sure we can solve it or not. So as for the second question, since the patient just is going to lay down, so we just lay down the connect, just have it rotate.
Right. So now, yeah, exactly. I see what you mean. If the connect's lying down, the patient's lying down, they're on the same plane, and so you can track it. Yeah, absolutely. Did you want to? Let me give you my.
Thanks, Krishna. Yeah, I think it's just worth emphasising that we see Connect technology. Connect technology is in very early days for everybody that's working on this, not only from an application point of view, but also those working on SDKs and so on. So what I want to highlight is that Microsoft's keen to hear your feedback on what features you think are missing today or would enhance your application. So if rotation, for example, rotation detection is important to you, your application, then do let us know, either through the forums, which is a great way. The product group read the forums all the time. They're on there. They're supporting people through the forums. We really want to hear what sort of features that you would like to see in the SDK. Where, in particular, they are software features, and rotation detection might be possible to do by software rather than new hardware. Then those are the things you can imagine that we can prioritize to put on future versions of the SDK. And the more people that ask for that feature, then the more chance that that feature gets included. So I just wanted to emphasize the point. Don't think of the SDK as something that's fixed. It doesn't have something. But we're open to feedback. We want to hear what you would like to see in the SDK. And while we can't promise to implement the features that you want immediately, it really helps us in understanding what the priority is for the researchers, for the applications, the companies that are thinking of using this. And rotation is a great example of that. We're very early days in the SDK. Everybody's trying to put in as many features as possible, but you tell us what features you would like to see.
Absolutely, yeah. The one other thing I would probably add to that is there's again a very strong community around Connect, and so if a feature actually bubbles up, what we've seen in the past is the community actually take a shot at solving the problem, right? I mean, on top of the official SDK. So you'll actually find a bunch of libraries. In fact, one of the sites that I forgot to show that I wanted to show, apart from the Connect for Windows and the channel line sites, is a site called Codeplex. Are you guys familiar with Codeplex? How many of you are familiar with Codeplex? A few folks, right? Codeplex is basically a shared source. We call it shared source repository. So in all technical purposes, it's like open source repository for Microsoft technology source code, right? So only source code lives on the site. And so what you can do is, if you come into Codeplex and search for Connect, because remember, Codeplex has source code from every technology that we make. But if you search for Connect, you can actually see there's like about 80 projects that's been submitted by the community around Connect, and you can actually see that a bunch of those projects actually are toolkits or libraries. So for instance, there's a Connect toolkit here. Somebody's introduced a toolkit for making the Connect into a mouse cursor and so on and so forth. So like for instance, here's one on using it to control PowerPoint. But the point is, if a certain scenario bubbles up, more likely than not, we'll actually see the community actually get in on it and build a toolkit around it. Or we encourage you to actually take a shot at it and throw it here, and then have the community help you iterate and refine it further as well. So yeah, it's one of the advantages of having a sort of nice ecosystem supporting the official SDK. So yeah, definitely. And while we're on the topic, I think one of the ways that personally I would try to solve that problem is if you do Connect chaining. If you have more than one Connect observing the subject, then you can actually, between the two Connects, you can identify when the user actually moves away from one Connect into the other. Because what will happen is the skeletal tracking will actually shift from one Connect to the other. So say for instance, I have a Connect at two Connects at 90-degree angles. When I move away, this will lose skeletal tracking, and the other Connect will gain skeletal tracking capability because it can see me in sort of the front position. And so it is possible to write some custom code to track the user's rotation if you chain multiple connects. An other option could be if you combine the skeletal tracking feed with the feed coming from the VGA camera, and if you write some basic intelligence to figure out from the VGA camera if the bird is seeing. Because what the Kinect allows you to do is when it returns the position of a joint, say for instance the joint we care about is the head, right? So the skeletal tracking system will basically return the information of where it thinks the head is. There are certain APIs that allow you to take that information and correspondingly match it to the corresponding pixels in the VGA feed. So what you could potentially do is you could isolate the segment, the head segment alone in the VGA feed, pull that, and if you have some basic intelligence, if you write some code to identify if that's the front of the head or the back side of the head, right? That can give you a sort of a makeshift rotation awareness system with just one connect instead of chaining multiple connects. So there's approaches, but again, the official SDK as of now is useful. Thank you. All right, any other questions, thoughts, comments? Okay, so we have, before break, how much time do we have? 10 minutes? Okay, so that's perfect. So what I'm going to do in the next 10 minutes, because I think we're going to go on a lunch break and then come back and sort of pick up where we left off. But in 10 minutes, let me do this. Let me show you what you get when you download and install the Kinect SDK. So when you download the Kinect SDK and install it, it installs it inside the program files folder, inside this folder called Microsoft SDKs, in its own folder that it creates called Kinect. So the program files in Microsoft SDKs folder will already be on your computer, and then Kinect, when it gets installed, will create this Kinect folder and a subfolder for the version number. The latest version now is beta 2, and that's what we're seeing here. And everything in the installer gets expanded here. So the good thing is that the files do not go to multiple places. It all comes and lives here. And in here, you'll basically see all of the things we looked at. You'll actually see the actual drivers for each of the 4 hardware subsystems inside the Kinect. So these are actually the device drivers. So that's an important thing. Install SDK before you connect the actual Kinect device to your PC, because otherwise the drivers will not already be in place. So you'll get the drivers, you'll get some documentation on sort of the programming API. You'll also see some samples in a zip file. You'll actually, let me open it and show you what you get. So you get some samples, both managed samples and unmanaged samples, which is both .NET samples and C++ samples, for doing things like audio and how to record audio and how to do beamforming on audio, how to use a skeletal tracker system, like a vision system, the camera system, and you get basically a full game. In fact, it's called the Shape game that actually brings all of this together: the audio subsystem, and the vision subsystem into an actual playable game. And obviously, the Microsoft the license agreement across all samples and across all code and codeflex and all of that states that you can take this code and use it any which way you want in your own application. So feel free to reuse or modify this code is what we said. The 2 most important things we care about are the actual libraries that you use to program Kinect in your own application. If you're writing C++ programs, your libraries are going to be in these 2 files. The files called INC, the include files, and the lib files. So INC has all the header files that you will bring in, and the lib files actually, based on your platform, whether it's an AMD or an x64 platform, has the lib files that you include in your C++ project. If you're doing .NET, the library lives in this folder called assemblies, and it's just this one DLL file called Microsoft.research.kinect.dll, right? And this contains all of the the types in the Kinect SDK that you can program against. And And given that we're going to basically be, for this session at least, programming in C# and .NET, I will take the next 5 minutes to show you what is inside the Connect SDK. And to do that, I'm going to use a tool called the .NET Reflector. How many of you, actually let me ask you this, how many of you program .NET here? C#, VB? A few hands, okay. So you probably are familiar with Reflector already. Actually, another question that I wanted to ask early on, how many of you have done any level of programming with the Connect? Like how you've played with the SDK? There's about a few people already. Okay, that's fantastic. So that's about 6 to 8 people that I saw. Okay, that's great. So, with .NET Reflector, for those of us that don't do .NET, that haven't programmed .NET, basically what .NET Reflector does is think of it as a disassembler, right? It can take a DLL file, a library file, or a program file, and break it down and show you the individual classes and interfaces and even the actual properties and methods and even the source code for the properties and methods. So what I'm going to do is use .NET Reflector to open my Connect library file, so Microsoft.research.connect.dll. And so what this is going to do, okay. So what I did was basically, let me do it again because I don't think it was very clear because I have another window going. So let me delete everything. There's nothing in the Reflector file. Reflector window. I'm going to say go File, Open Assembly, choose the Microsoft Research Connect DLL file, and open it. And what this does is it loads the library inside the Reflector window. And when I expand it, it shows me all of the different namespaces and classes and methods and properties inside that library. I actually see that these are the 3 big namespaces, right? A namespace is just basically a big bundling of functionality of classes and interfaces in a logical sense. So for instance, in the Connect library, you can see that there are 3 namespaces. And if you cannot read in the back, all the way in the back, let me read it out for you. There's Microsoft.research.connect, there's Microsoft.research.connect.audio, and there's Microsoft.research.connect.NUI, NUI standing for Natural User Interfaces. The first one is just blank, it's just a placeholder namespace. But you'll see most of the functionality inside Microsoft.research.connect.NUI, which basically controls all of the camera subsystems, your VGA camera, your depth camera, your player segmentation, the humanoid shape detection, obviously, and the skeletal tracking. All of that happens here. And all of the audio stuff in terms of beamforming and other features of the multi-array microphone like echo cancellation, noise suppression, all of that happens here. But just to give you a perspective, you can look at the amount of functionality in the audio segment versus the amount of functionality in sort of the camera subsystem, right? And the reason again for that is because most of the audio functionality is already built into Windows, right? So the Connect SDK didn't have to reinvent all of that. So for most of the SDK, it's going to focus on the NUI subsystem, which is actually all the camera stuff. Now inside the NUI namespace, I'll make it slightly bigger so we can see more. You see that this, all of the classes, all of the interfaces, all of the other types are listed right there. And what you see is basically what there is, and that's it, right? And if you've done any sort of .NET programming before in any language, whatever type of application you build, you'll realize that this is a very compact namespace. There's only a few types and that you worry about, and literally everything that you program on the Connect has to do with these types. The most important class that you will always start with is this class called runtime. And let me expand this to show you what's inside runtime. So for those of you that are that can read C or C++ or C#, you'll actually see that this looks very similar to actual source code, in fact. When you write a class, you basically, have this class declaration like public class, whatever class name, and then inside the class you have all of your methods and properties and variables and stuff like that. It looks very similar to that, right? So that's what Reflector does. It basically takes a library and breaks it down. In fact, you can even expand all of the methods. You see all of these methods here. You can even get their implementation if you want by just clicking here. When I say expand methods, what it's going to do is it takes that class and breaks it down into the exact functionality as a developer would have written it. So this is basically all of the source code of this class, if you will. And this is a great way to learn C# or .NET programming, is by taking existing classes and see how it's actually written. But let me collapse it back so we can actually read all of this in one screen. And let's look at what runtime class offers us. Again, this is the one class that represents all of Connect, right? All of the functionality you can access using the cameras inside the Connect is all right up here. And let's, in the next 3 to 4 minutes, look at what's in here. If you look at, let's start with the properties first, because it gives you an idea of all the properties you can extract from the Connect. You see that basically it exposes a few properties, the most obvious of which is the video stream, which is the raw stream from the RGB camera, and the depth stream, which is a raw feed from the depth camera. It also exposes some metadata type information like instance index and instance name, which basically, if you're chaining multiple connects, it'll allow you to identify one connect from the other connect and so on and so forth. It also has a status property which tells you if the connect is initializing, if it's running, or if it's shutting down, and so on and so forth. Literally, that's it. The two obviously important properties are the depth stream and the video stream, which is basically going to return to you the raw data from the cameras. In terms of events, you'll see it actually exposes 3 events. An event is a mechanism in .NET, as in C++, to indicate that something is ready or something has happened and is ready for consumption. And so Connect runtime uses these events called video frame ready and depth frame ready to indicate that a frame is ready to be read from the video camera or the depth camera, right? So literally, this is the programming model, as simple as this. You basically, and we're going to come back and actually start coding right after we come back from lunch, but basically the structure that you will see us take is this. We will create an instance of this class called runtime, and then we will use methods like initialize to initialize our Connect, and then we will wait for these events like video frame ready and depth frame ready to fire, because that means it's telling us that the camera has read a frame and it's ready for us to consume it. And then we will use these properties, the video stream and depth stream, to actually read that into our application and consume it any way we want. Right? In our app, we probably try to show it on the screen, but if you're building a game application, you can use the depth stream and or you can hook into the skeletal frame ready event and get this joint information and do gesture tracking or whatever you want to do, right? But this literally, what you see in front of you is the API. And like I said, if you've done any level of programming before, you realize that this is an extremely simplified API, right? So it's really easy, it's really intuitive, as you'll see when we come back and start coding. So with that, I think from my perspective, I'm good on the content I wanted to cover before the break. But if there are any questions, I'm happy to take that now. What we're going to do after coming back is actually get into the Visual Studio editor and start writing code. But any conceptual questions before that, I'm happy to take now. Okay, so was there a question there? No, okay. So with that, we're ready to go on a break, and I turn it back to you.
Okay. Thank you, Krishna. 我们掌声谢谢 Krishna。好，那我们接下来呢有1个 小时的午餐的时间，要麻烦大家拿着您的午餐券，然后移驾到门外去领取您的餐盒。那因为我们今天到场的人数很多，要麻烦坐在右手边的来宾从右边的门出去拿餐盒，左边的来宾呢就从左后方出去拿餐盒。那麻烦大家。